volumes. It'll be crazy when we do our last section ever.
I know, it's so weird. And I was just thinking about, like, we have one section of vocab left. That's weird, too.
Yeah. Like, is it like a section or the review?
It's a section. So.
Should probably give you sentences.
I hope not. I hate those ones. They take forever.
Well, we were supposed to get, like, I think we were supposed to have a test that, like, that's writing a few sentences in the notes.
Fun.
Yeah.
But she gave us the wrong one.
That's always good.
Yeah, we got lucky.
All right, the volume of a solid of known integrable, I can't even spell, integrable cross-section area A of x from x equals A to x equals B is the integral of A from A to B. So the volume is equal to the integral from A to B of A of x dx. And so basically, like, the notes are going to be explaining how to find the volume for, like, different cross sections, and, like, what that looks like. And some of them are much harder than others. So when you get those ones, you just get sad. But that's okay. How to find volume by the method of slicing. So this is the first one. So I'm going to write the little steps, and then over here on the side I'm going to draw like the little picture that goes with it of what this would look like. So first we sketch the solid. And a typical cross section. This is basically like a prism that's sideways. May not really look like it, but that's what it's supposed to be. Let me move my dotted line maybe. Let's move it there. I don't know. That doesn't really make it look any better, but we're just going to go with it. So our cross-section area is there. So it's like if we like took a slice out of it, that's what we're looking at. So then we are going to find a formula for A of x. 3, find the limits of integration. So the a and the b. And then 4, we integrate a of x to find the volume. The next one is circular cross sections. And there's not much difference in this one and the previous one, so all I'm really going to do is write the difference. So the only real difference when cross sections of a solid are circular is the formula for area, or the formula for a of x. Which, I mean, I feel like that's pretty self-explanatory, but nonetheless. And we're going to ultimately end up looking at solids of a revolution. And this will kind of like play into that as well.
Is there a picture for that one?
Yes, I'm getting ready to. I was making sure I wasn't missing anything. So this one's going to kind of look like a flower vase, at least the way I'm going to draw it. Obviously, there's all different pictures. That's what I'm doing, so. Not a great vase, but close enough.
Oh, that's a fish.
Okay. My cross section is not straight. Okay, that's as good as it's gonna get.
You said it was supposed to be a vase.
I mean, yeah. Like that would be an example. Is like a vase, but obviously a vase that's not hollow in the middle.
What's at the top of like a bowling pin? I was about to say a rolling pin.
Yeah, top of a bowling pin would be another. The pictures of these things in the book look much better, so if you want like a better visual, look at the book, but I just try to give like a little reference of what these things would look like when you're going through. So the next one is a washer. You know, like the things that you put on like around a screw. Yeah. Not like the thing that you clean your clothes in.
Or your dishes.
Yeah. So the washer cross section. So the area of a washer is pi r squared, that's big R squared, minus pi little r squared. Or we could factor this out and do pi times big R squared minus little r squared. And I always like to point out, which I know y'all are aware of, but a common error is that people try to write pi times big R minus little r squared. So they try to square the whole thing, but we have to square each piece individually first. Because basically with a washer, we've got, you know, your big circle, and then we've got our little circle, which that's not.
So is that our picture for this one?
There's another graph too, but that's gonna be farther. Well, I'm gonna I have one more thing to write, and then I'm gonna do that one. So, but little r is this inner one, and then big R is the outer radius. So if I can get my words right and not mix y'all up like I did in the last chapter, it's outer minus inner. Because we have to, obviously, we're removing that middle area where there's nothing there. So, well, I'll write it, but I think y'all got this. But area for a washer is found by subtracting outer from, nope, hold on, I'm about to say it backwards again. Subtracting inner from outer. Does outer have one T or two?
One.
Okay. I wrote it that way, but then I was like, wait a minute, that looks weird. And then I wrote it with two, and it still looked weird, so I wasn't sure. Let's see, each cross section perpendicular to the axis of revolution. So I can write a picture. Is a washer which is a circular region with a circular region cut from its center. Again, I feel like y'all know that, but I'm more doing this for future years, people that may or may not know what that looks like. My graphs are just going to get progressively worse looking. I'm just going to warn you because of what they look like. But I'm going to do my best. So I've got basically like a cup that's like rounded, but it's not actually going to be a cup. But it's kind of what it looks like. Close enough. And then basically within that, I've got like an area out of it. I know this isn't symmetric, but it's close enough. I guess technically this is going all the way through. There. So then my washer is going around, and then I've got the inner part of it here that's being removed. Just pink. Cylindrical shells. Another way to find volumes of solids is, of rotation. That can be useful when the axis of revolution is perpendicular to the axis containing the natural interval of integration. So the next the one of these pictures, I'm not even gonna make an attempt at drawing, because I tried last year and it kind of looks like a gumdrop. But is a bundt cake. I presume y'all both know what a bundt cake looks like, right?
A little buntini. I like buntini.
So basically, if you had like your bundt cake, it's obviously like the middle is hollowed out, and so like that area around, that would be what this is for. Another option that's easier is if you've ever had, like, not if you've ever had, I'm sure you've had a roll of paper towels, like just think of that, but like the tube, but like let's say that it was like thicker, then that would allow us to find the volume of like the roll itself. So or like an actual roll of paper towels, not just like the middle of it, technically, for that too. I mean, paper towel is kind of a weird thing to like think about that for, but so that would be more like if it's and then we just had like a thicker band around this one to see it. Anyways. And it's like rotating around.
Is that a picture for that one?
Yeah. There is another little picture that kind of goes with this actually, but it ties to this, but again, well, I might be able to put it all in here. Let me see. So this line here is hold on, make make sure I've got this right. Yes. The shell height. The dimension off of the x-axis here is the shell radius. Which is y. And then the shell thickness, which would be this part that I colored in a little bit more, is dy. And this is just x equals y squared here, but only the positive part of it. The book shows like these things that I've written in red is like a two-dimensional thing as well on page 406. That might be helpful to look at too if you feel like you're thoroughly confused. And then whatever like this like height is here of the radius, this is also going to be your integral of integration. So like our, basically like the dimensions that we're doing it on.
Was that supposed to say integral or interval?
Interval. There we go. So then the formula for this one is V equals, this one's probably my least favorite, 2 pi times the shell radius times the shell height times dy. And there's like obviously other kinds of cross sections too. Another one that you could see, I mean there's a ton you can see, but one that would possibly come up in our stuff is one that kind of looks like a mountain. And then your little cross-sectional areas would be like this, like it's hard to draw them, but like the rounded areas there. Anyways, there's a ton of those, but that's it. And then we'll get into like some of them they'll ask us to like look at the different cross-sectional areas and like shows what happens with them and stuff like that. So to find the volumes. Washers actually probably are my favorite. Shells are definitely my least favorite. And the other ones are just like area and putting them in the formula, so anyways, but we'll pick that up on Monday, probably, I mean, at least Monday, Tuesday, and then do y'all have a track meet next Thursday? Okay. I'm guessing you're probably leaving early, but I don't know.
I think 1:30.
Okay. So you'll probably, you'll be here for a little bit of this class probably, so that may just be a review day, and we may be quizzing on Friday. Because I'm suspicious this will take us into Wednesday, but it just depends how quick we get through it. The last section's super short, so if it does a little bit, we may use like Wednesday or Thursday to do some like review of others, like, or maybe to go over those practice tests that y'all took, if we do finish this on Monday and Tuesday, so.